Okay, so welcome to the next session of this morning. The last one before the free afternoon. And we start with a talk by Delon from Paris 5.
Exactly.
I always get confused with the numbers.
Descartes.
Descartes.
Université.
Okay, the talk is on high-dimensional mixture models.
So hi. First, I would like to thank the organizer for inviting me, even if I think that there are far too much French people here. Okay, so I speak French since Monday, so I cannot. English is difficult when you speak French all the time, so next time invite only me, and it will be better. Okay. Okay. So this talk is very linked to the talk of Mila, because I will speak about prior for patch-based method in image restoration, and with a special focus on image denoising. And I will finish with a work on high-dimensional mixture model for unsupervised image denoising, and this is a joint work with my colleague Charles Bouveron and Antoine Houdard. So, just a small recall on patch-based restoration or patch-based models. So, I think that this model appeared around 12 or 15 years ago, both in image editing and image restoration. And we can say that this model tries to represent images by sets of local neighborhoods or patches. And the idea is that for each pixel of your image, you extract a square patch. It doesn't have to be square, but to simplify, assume that it's a square patch around your pixel. And you extract it, so if it's a 10 by 10 patch, you have a vector in a high-dimensional space of size 100. And if you do that for all patches in your image, okay, and another one, at the end you have a cloud, a huge cloud of vector in your high-dimensional space. And the idea of these approaches is to make all these vectors collaborate in this high-dimensional space completely independently, regardless of their position in the original image. So that's the main idea of these methods. And there is a nice expression due to Delon and Mumford, who said that patches are somewhat the analogs of the phonemes of speech. Okay, so there have been tens of thousands of papers on patch-based methods. So these are just a few of them in various domains, very various applications. But just the main idea of why these methods are powerful is that for each patch, the idea behind this method is that for each patch you assume that somewhere in your image, you will find other patches which look very similar to this one. For instance, here, I could take these two patches. And the idea behind, for instance, for image denoising, is that it's just the idea of the law of large number. If you average these patches, if you assume that these patches are just a realization of the same mean with just random noise between these three realizations, then when you average, you will denoise. Okay. So more precisely, if I take a very classical large class of inverse problem like this one, so I observe V through an acquisition. So I observe V, which is AU plus N. So here U is your clean image, your unknown. N is some kind of additive noise. And A is your acquisition operator. So for instance, so here you want to reconstruct U from the observation V, to estimate U from V. For instance, for denoising, A is identity and N is any additive noise that you want. For deblurring, A is a convolution operator. For missing data, A will be a diagonal matrix with 1 and zeros. Yes, I didn't say, but here U is seen as your image is seen as a vector. So A is a very, very large matrix. And when you use patch-based method to solve this kind of problems, you try to rewrite the same inverse problem, but directly on patches, so separately on all patches. So you hope that you can rewrite the previous problem like this. For each patch, yi centered at the pixel I of your image V, you assume that yi can be written ai xi plus ni, and you want, at the end, you want to estimate all clean patches xi from the observation yi. Of course, strictly speaking, going from here to here is only possible if A is diagonal, because if A is, for instance, for blur, it's not completely clear that you can write this kind of equation simply from the previous one if the blur kernel is larger, is too large. Okay, so a very classical way to solve this kind of inverse problem on images or on patches is to use the Bayesian framework. So as I said, it will be very similar, the first part of the talk will be very similar as what Mila told you. So what we do here is that we assume that our patch X is a realization of random vector X, large X, capital X, and you assume a prior distribution for capital X. And if I will assume here that my noise is white and Gaussian just for the sake of simplicity, but you can do the same kind of reasoning for any additive noise. So my posterior distribution, knowing y, will be this. So this is this comes from the Gaussian white noise, and this is my prior. And when I want to reconstruct x from y, ideally I would want to use a conditional expectation. Okay, this is the first strategies I can use to recover x, because it will minimize the risk. But in some cases, in most cases, it will be very difficult or tricky to try to estimate this conditional expectation. So what you can do is just try to compute a linear conditional expectation, which is much easier, or it's also called a Wiener estimator. And finally, you can, of course, also try to find the maximum of the posterior distribution, so the maximum a posteriori. And there is a very simple case where all of these strategies will coincide. It's always the Gaussian case in statistics or in probability, which is easy. So for Gaussian prior, if you assume that x follows the Gaussian distribution of mean mu and covariance sigma, and then x is independent from your noise n, then all of these estimators boils down to this affine estimator, affine function of y. Okay, so it's like a barycenter between your mean, the mean of your prior, and your observation y. Okay. So if we look at the recent literature on patch-based denoising, almost all the recent papers use this kind of framework, Bayesian framework with Gaussian priors. So basically, they take the noisy image, they extract all the patches of this noisy image, and then they try to infer some Gaussian model on these patches. So of course, you cannot have only one Gaussian for all the patches, so we will see how they do that. And once they have inferred some Gaussian models on these patches, they use it to denoise, and then from the denoise patches, there is an aggregation step, and Miller insisted a lot on this aggregation step in our talk, and you reconstruct your denoised image here. So let's see. There are two questions that can be raised in this context. The first is how you restore your image from the set of restored patches. So this is the aggregation. And the second question, and this is the focus of this talk, is how you estimate mu and sigma. So how you estimate the parameters of your Gaussians, different parameters of your Gaussian from the degraded patches, or from something else. Oh, sorry. Okay, so quickly, the aggregation. I know that Miller said a lot about this, so I will be quick, and it's not the focus of my talk. For the aggregation part, what you can do, the simplest thing you can do for a pixel I is to take the estimator coming from the patch centered at this pixel, and taking just the central value of these patches and putting it at this pixel. You can do better if you consider all the patches containing this pixel and aggregating the value coming from all these patches. Okay, so you can do this with equal weights, or you can do this with weights which are chosen in a clever way. Or so those are possible solutions. We could think of other solutions, but a third possible solution, which is the one chosen, for instance, by Zoran and Weiss in their paper EPLL, method EPLL, is is to rewrite the aggregation as a global optimization in U. So what they do basically is that they rewrite aggregation as minimizing this energy in U. So this part is just coming, this data fidelity term is just coming from the inverse problem. And here, the interesting part is that they write a prior on U through the patches. So this is P, this density here is in their paper is a Gaussian mixture model on the patches, and this gives you your prior on your image. Okay, so since this is a Gaussian mixture model here, this is not convex, so they use some kind of half quadratic splitting by introducing auxiliary variables z to minimize this alternatively on z and u. And at the end, basically, you end up alternating two steps. You update the patches with maximum a posteriori, and then you update your restored image by using your the previous version of your restored image and the aggregation of the current patches, and you go again to 1 and 2, etc. Okay. So I won't speak again about aggregation. In all my experiments, at the end, I will just average. I will just choose this averaging, but I agree with Mila that this is a very important step, and that it's often not. It doesn't receive the attention that it deserves. Okay, so now I had two questions. The first one was how do you recover your image from your patches, and the second was how you estimate your model, your Gaussian model. So let's go to the second question. The first possibility, which is the possibility we explored in NL-based denoising, is to estimate local Gaussian model, which means that for each patch in your image, for each patch y1, we'll try to find a set of similar patches, and from this set of similar patches, you will try to infer a Gaussian model. So you have a Gaussian model, basically in NL-based, you have a Gaussian model for each patch of your image. So that's why I speak about local estimation. And when you do that, so you use just maximum likelihood to compute your mean and your covariance matrix. When you do that, You have to be careful because your covariance matrix here is estimated from noisy data. So you have to remove, to estimate the covariance matrix of your clean patches, you have to remove sigma square identity. And so you have, like Mila said, you have a very high risk that you, at the end, you get some negative eigenvalues in your covariance matrix. So you have to be careful with this. And just to emphasize that this method is very efficient and very simple. This is a method implemented in the software DxO Optics Pro, which is one of the most famous photo editing software on the market. Okay, so the second possibility, so the first one was to infer local Gaussian model, and the second possibility is to estimate, is to try to write a global Gaussian mixture model for all the patches of your image. So you assume a Gaussian mixture model with k groups, proportion pi k, average mu k, and covariance matrices sigma k. And this model is used by several papers on patch-based denoising, recent papers on patch-based denoising. For instance, in the paper by Zoran and Weiss, they learn this Gaussian mixture model externally. They don't learn it on the degraded image, but they learn it on an external, very large image database. But they use it afterwards to restore their image. And in these other works, these two other works, this Gaussian mixture model is learned directly on the degraded patches. So for instance here, it's learned directly on the degraded image, but with some kind of regularization, because the Gaussian mixture model is initialized on synthetic patches. And in this work, it's very inspired by this. You also have a synthetic initialization, and it's important for the Gaussian mixture model to be good at the end. Okay, and I will speak about this later because it's the last part of my talk. Okay, so all of this is really nice, but there is a slight problem. I said earlier when I spoke about Unsupervised that estimating the covariance matrices from the noisy data is not always easy, but it's worse than that, because when you do that, you suffer from the curse, the famous curse of dimensionality. So I hope you like my. Okay, everyone understand this little figure? Okay, so my illustration of the curse of dimensionality. So it's not mine. It's my PhD student who did that. So when you try to estimate a covariance matrix from the sample covariance matrix of your data, you have several problems. First, on one hand, so you assume that you are in high dimension. For patches, for instance, you are in dimension 100, but you know that points, so your patches in these high dimensional spaces will be completely isolated. For instance, it's a very classical computation. If you want to capture, assume that you are in the unit hypercube in dimension 100, in dimension p, and you want to capture a fraction s, for instance 1% of the volume of this unit hypercube, then you need a smaller hypercube of edge length s, so s is a fraction, to the power 1 over p, okay? And if you take s equal 1% and p equals 100, then s to the power 1 over p is 0.95, sorry. Which means that just to capture 1% of your data in this unit, if your data is distributed uniformly in this unit hypercube, just to capture 1% of your data, you need a hypercube which is really, really large, okay? Which is almost intuitively, we think of this edge length as almost as large as 1. So it means that you don't have the notion of neighborhood, of local neighborhood, completely disappears in high dimension. Donc it's completely counterintuitive. So if you think about this for your patches, even if your patches are not distributed uniformly in the hypercube, it seems possible that around one patch you have nothing. Okay, the closest patches around it are very, very far from it. So on the one hand you have this, but on the other hand, if you want to estimate your sample, if you use a sample covariance matrix to estimate the covariance matrix of your data, the number of sample n that you have to choose must be very large, because if it's not large enough in comparison to p, the dimension of your space, then the estimates, the sample covariance matrices estimate will be, they can be ill-conditioned or they can be singular. And it's even worse than that. Even if your number of sample n is very large, we know from the random matrix theory that the convergence of your sample covariance matrix to the true covariance matrix of your data is not a convergence in spectral norm. So it means that the eigenvalue of your sample covariance matrix won't converge to the eigenvalue of the true covariance matrix of your data. So it's not very nice for us, for what we want to do. So some possible workaround would be to reduce the dimensions of the space, so you can use small patches, for instance, or you can use Gaussian model with fixed lower dimension for each Gaussian model. So it's what is done in short PLE, for instance. And it's also what we do in the model HDMI, but the difference with this work is that we infer automatically the smaller intrinsic dimension for each Gaussian. Or you can use some kind, try to use some kind of regularization or hyperprior to stabilize your estimation. So either regularization or parsimony, or dimension reduction. Those are your three possibilities. So just a word on HBE, which is an hyperprior based estimation for Bayesian estimation for Gaussian model. So it's a work we made a few years ago, but it was only published this year. So what was the idea here? So here we come back to the local Gaussian model exactly as like in NL Bayes, but you will try to stabilize your estimation of the local Gaussian model. For instance, if you don't want to do denoising, but if you want to do restoration because with noise and missing data, if you have pixels who are missing in your data, then you cannot apply NL Bayes, for instance, because you cannot directly infer covariance matrices from your data. So what you can do is that you will assume you will assume some kind of hyperprior on your Gaussian parameters mu and sigma. And what is classical in statistics is to assume a conjugate hyperprior for mu and sigma. So it's here it's a normal Wishart distribution on mu and sigma. And if you do that, you can directly rewrite everything as a huge, a larger maximum a posteriori problem, where you maximize both in the patches that you want to reconstruct and in mu and in sigma. So you write this like this, and at the end, maximizing this complete maximum a posteriori is equivalent to minimize this function. And so here lambda is the precision matrix, it's the inverse of sigma. And minimizing this function is, well, I'm not able to find a global minimum, but the function has is biconvex in both xi mu on one end and in lambda on the other end. So you can use an alternate minimization scheme to minimize it. And when you do this, it converges in a few iterations. And you can show that your sequence converge at least to a stationary point of f. Okay, so I don't explain everything about this work. Of course, it's not. So this is a nice way of explaining it, but of course the initialization is very important. So there are a lot of tricks to make all of this working. This is a proposition about the convergence, and at the end, it's still it gives pretty nice results. So here, for instance, for interpolation, so this is a ground truth. This is my image with missing pixel with no noise. And I just want to interpolate this, so this is the result that we get with this approach, and this is the result of the piecewise linear estimators of U, Mala, and Sapiro. So using this hyperprior gives you much more information here. Well, this result is already quite nice, but this result is nicer, I think. Same thing here for missing pixels, and an experiment with missing pixels plus Gaussian noise, a small Gaussian noise. So the result is here from these images, from this image. And this result here is interesting because on this boat image you have very fine structure here that that are better recovered here than in the piecewise linear estimator approach. Okay, so I try to be on time. So, oh no, I still have 20 minutes. It's okay. Okay, so I will slow a little bit. I don't know why I thought it was later. Okay, so let's go back to our Gaussian mixture model, and I will try to explain what we try to do with the HDMI model. So here, our idea is to try to circumvent the curse of dimensionality by constructing a Gaussian mixture model where each Gaussian has a lower dimension, which is estimated in the inference of the model. So you still assume a degradation model, classical degradation model with a Gaussian white noise here. And what you do to model this lower dimension groups is that, okay, first I will call Z the random variable, which is of course unknown, which indicates the group from which the patch X has been generated, and I will call pi1, pi k the proportion of the group. And what you will assume is that the patch X, so your unknown patch X, you assume that it lives in a low dimensional subspace, which is specific to its latent group. So if Z is equal to K, then X is equal to uk t plus mu k, and here mu k is just the mean of your group K. uk is an orthonormal transformation of size, so it has p rows and dk columns, and so dk here will be the size of your group, the intrinsic size of your group K, dimension, sorry, not size, but dimension of your group K, and t, the latent factor t, you assume that conditionally to z, t is Gaussian with mean 0 and covariance matrix lambda k. So the covariance matrix lambda k has dimension dk. So is that okay? And if you assume this model, then the distribution of y, so y is your noisy data, is also a mixture of Gaussian with the same number of Gaussian, the same proportion pi k, the same mean mu k, and the covariance matrices becomes this. Okay, so this was the covariance matrix of your t here. uk is your orthonormal p times dk matrix, and here you take the noise into account. And if you rewrite uk, if you complete uk in a p times p orthonormal matrix that you call qk, then qk transpose sigma k qk is equal to this diagonal matrix, where in the dk first lines you have real eigenvalues, which are lambda kj plus sigma square, and in the last p minus dk eigenvalues you only have sigma square. So in this model, the intrinsic dimension of your group is dk, and you assume that in the p minus dk eigenvalues you only have noise. They only take into account the noise, accounts for the noise. Okay? So this model is a generalization of the full GMM, since if you choose dk equals to p, you find the usual Gaussian mixture model, and it has very strong links with the mixture of probabilistic PCA model, with the difference that in MPPCA the dimensions of all Gaussians are the same, whereas in our model the dimension of each Gaussian has its own intrinsic dimension. Okay, so under this model it's very easy to denoise, because with a Gaussian mixture model the conditional expectation is explicit. So the conditional expectation of x knowing y is only a combination of affine. So this is a affine estimator in the group K. So if you assume that you are in the group K, you have the Wiener estimator under this Gaussian model, and you just have to combine all of this affine estimator with weights here, and these weights are just the probability to belong to the group K under the observation. Another nice thing here is that if you look at your Wiener estimator, so this is the traditional formula for the Wiener estimator, with here this is the full covariance matrix, p times p covariance matrix. If you rewrite this equation, you can rewrite it like this, and here you see that you don't have any matrix inversion anymore. It's much more numerically stable, because here this matrix delta k is only a diagonal matrix. So it's very, you don't have any numerical problem when you inverse this. Okay, so now that we have our model, we know how to denoise with this model. So how can we infer this model from the data? So what we do in practice is that we use just the degraded data to infer this model, but you could do it like Zoran and Weiss, you could do it on an external database. You can do everything you want. So what you have to do is that you have to estimate your model parameters, the proportion pk, the average mu k, all the eigenvalues a, k, j, your noise variance sigma square. If you don't know it, you have to estimate it, and of course your eigenvectors qk. And you also have to determine the hyperparameters of your model, so the number k, capital K of groups in your mixture, and of course the dimensions dk of each group. So classically you cannot maximize directly the likelihood, so you use some kind of you use expectation maximization algorithm to estimate all these model parameters, and I will explain after how you estimate k and the dimensions dk. So just for expectation maximization, there is nothing new here. It's just the classical EM. So on the expectation step, you estimate the probability to belong to the group K, knowing your observation and your current set of parameters. And on the maximization step, you recompute the maximum likelihood estimator for the proportions, for the average, and for the covariance matrices. Okay, nothing tricky here. And for your hyperparameters, what we observed is that the hyperparameter k, the number of groups, is not a very sensitive value, so I will show an experiment later. So in practice, we set k to a given value, for instance 100 or something like this. But an important so it's not important. K is not very sensitive, but the dimensions d1, dk are. So to choose the interesting dimensions dk, we have two cases: a supervised case where you know the noise variance, and then you have an heuristic that links dk to the noise variance. And if you don't know your noise variance sigma, then what you do is that you do this for several values of sigma, and then you use model selection to choose the best sigma. So about this heuristic, when sigma is known, actually, so I don't know if you remember. Okay, if you remember this, the form of the covariance matrix once it's diagonalized. Here, clearly, the dimension dk is linked to sigma because p minus dk last eigenvalues are all equal to sigma square. So a good estimator for sigma square is the average of the last eigenvalues in your matrix. So in practice, if you know sigma square, you can estimate the dimension dk by this. Okay? So it's just the average of the last dk will be the dimension which minimize the distance between sigma square and the average of the last eigenvalues in your matrix. And when you don't know sigma, you do exactly the same thing, but for several values of sigma, and you use BIC, the Bayesian information criterion, to choose the best sigma for your model. And it's quite well adapted for the selection of sigma, because if sigma is too small, the likelihood will be good, but the complexity will explode. And if sigma is too high, the complexity is low, so this is low, but the likelihood is bad. So in practice, it's the BIC works well to choose sigma. Okay, so have 10 minutes to show you experiments. So here, just I told you that the choice of k was not very sensitive. So here for several values of k, I show the PSNR obtained when denoising the image Simpson with noise standard deviation equal to 10. So what we see here is that first it was surprising to us that even with very small number of mixture in the number of Gaussian in the mixture, you obtain PSNR values that are not bad, well, and not so far from the best PSNR value that you can obtain with the method. And it was also quite surprising to us that finally the PSNR values that you obtain, even when k goes from 3 to 600, for instance, are not varying very fast. So at the end, what we do is that we choose k around 40 in our experiment, because of course the larger k, the higher the computational load. But in practice, you could use a very small value for k to get a very fast acceleration of the algorithm. So this is about k. About sigma, here what I show is this is for the Simpson image, and this is for the classical Lena image. What we show here is two curves. So first a PSNR curve and a BIC curve for different input value sigma. So you run the algorithm for different values of sigma, and you compute the PSNR and you compute the BIC. And what you can observe is that both curves attain their maximum almost at the same time. So it means that the BIC is quite a good way to choose sigma, and it's true here and also here. There is a slight shift between both curves, and what we think that so here the BIC attains its maximum a little after the maximum of the PSNR. And since in image denoising you are always adding yourself noise in your images, what we think is that the difference between the true value of sigma that we added and the estimated value of sigma is due to the intrinsic noise in the original images, because in Lena, for instance, you already have noise before adding your synthetic noise. So in a way, we estimate that the noise is a little bit larger than the noise we have added to the original image. Another experiment here, just to illustrate the role of the intrinsic dimensions. So your clean image. So just a word about this image, because I didn't see it before. I was tired about people showing just Lena all the time, because it's a quite sexist image. So I created this one. So this is Homer Simpson. He is doing some cleaning while Marge is sipping a cocktail. So I encourage everybody to use this image instead of this one. Of course, there is not much texture here, so I have to do other images. Okay, so I stop with this comment, but well, I think it's important. So here, what we see. Here I show for each pixel, I show the most probable group in the mixture, the dimension of the most probable group in the mixture. So you see that for pixels which are in very flat areas, the dimension of the corresponding group is quite small. Here it's 10. So here these groups, these pixels must belong to groups of very low dimension, And you can see that as soon as you have texture and much more complex structure, then the dimension of the group increase. Another experiment illustrating the same aspect. Here, so in red here, you see a set of pixels belonging to the same to the same group in the mixture, which means that they have the same most probable group in the mixture. And on the right, we have sampled some patches from this group. So those are not patches from the image. Those are patches sampled from the Gaussian estimated from the Gaussian of the mixture corresponding to this pixel. Okay, so this Gaussian corresponding to this pixel here in red was a Gaussian of dimension 13. It's always 10 by 10 patches, so you are in a 100 dimensional space. So here, for the texture on the trousers of Barbara, you have a dimension which is larger, much larger, and here is a group with a class of dimension 0 for very flat regions in the Simpson image. So the benchmark is not the most interesting thing in the world, so this is just a p-scenar comparison tab for several images, several values of sigma, and in comparison with NL bias mostly, with or without the flat area trick. I think Milan told you about this trick where you have a special treatment for flat regions in the image. So the conclusion of this is that the PSNR are quite similar in practice. So they are slightly better with our approach. What was surprising to us is that the unsupervised approach is very good. So even when you don't know sigma, you are competitive with respect to NL bias, for instance. And a few visual experiments. So original images here, the noisy images with sigma equal 30. So here is it's what you get when you denoise with NL bias, with the flat area tricks enabled. So the flat areas are particularly smooth with NL bias. And here is what we obtain with our approach, the supervised one with 90 groups. So what's interesting here, so in flat areas it's less nice than with NL bias, I think. But what's interesting here is that in some texture areas we get much more information. We reconstruct much more information than NL bias, which is too smooth here. Okay, and I think I will stop here. And since some people have made some advertisement for their lab and for their work space, I will just show you. This is the view from my lab. It's not from my office, but we have some balcony. When the sun is shining, you can go on the. Well, the sun was not shining; it was it was at night, but it's a very nice place. And this is a view from our balcony. So come and visit us. You will be very welcome. And the preprint is available on archive and.
Thanks a lot for the talk. Are there questions? No.
On slide 21, can you decompose in this way every image? Every observed image. Are you sure that you can decompose it in this way?
You mean, what do you mean?
You
Can
have a
can I use, can I run this algorithm on any image?
Is it possible to have this decomposition for any image?
But this decomposition here, you mean this one?
The whole one, with the A, the M key.
But it's not
It's
related
a model.
to
I
the
know
fact
that it's a model, but it's important to know.
your input data is not the image. Your input data is a set of patches. So once you have a set of data in a high dimensional space, and you can always run this model. Does it make sense? It's another question. But
if you can generate the Y, if you can generate the Y, if you input the P, A, mu, D, and Q.
I'm not sure I follow you.
Okay.
I'm not sure I follow your question.
Okay.
You mean does the model make sense? Or you mean can you run it on any...
In both directions, if you can run it.
In
both directions.
In both directions?
Yes. If you have the entry A and mu and so on, can you generate a realist Y? And respectively, if you have an Y, are you sure to always have the P, A, mu, and so on?
Okay, so what we did, I think it's related to your question, you will tell me. What we did is that we made the following experiment. We learned this kind of model on an image, and then we completely forgot about the image, and we tried just using the model, so the TIK and the covariance matrices and the Gaussian mixture and the knowledge that each pixel has given probabilities to belong to each group of the mixture, and you try to reconstruct your image just knowing this. And it's very interesting because what you get is some kind of very smooth version of your image, which is very good in part of the image which are well represented by the model, well learned, well estimated, but in part of your image which are rare areas, for instance, the model is not good enough, and then you are too smooth. Is it related to what you asked?
Absolutely. But this is in the center of the approach, so that's why I was
absolutely.
Question, yes, please. What is the complexity measure that you use when you do the BRC discount parameters?
Yes.
Sorry, what is the
complexity measure?
Yes.
This psi of
that you use?
Model. Discount parameters?
Yes, exactly. We just count parameters, yes.
Because
it might not be the better idea.
No,
I know. Yeah.
And
actually, before that, we tried to use the BIC for choosing K, capital K, and it wasn't a good idea. So we tried other model selection tools, but we didn't really converge on this.
I can tell you.
Okay.
And I have another question, because your discussion about the noise, you were arguing that the reason why it works better with slightly stronger noise is because there is already some noise in the clean image, in the supposedly clean image. But that would just give it the other way around, right? Because since you're measuring MSE or PSNR with respect to the original image, which has the noise,
no,
you expect to give it the...
I agree. It's not exactly what I said. I said that the blue curve, which is the curve of BIC, finds a noise which is slightly larger than the noise that we added. But this blue curve doesn't see the PSNR.
But what's interesting is that also the PSNR is higher when you have higher noise than true one.
Yes. You mean, okay. You're right. So you mean that the PSNR is also shifted.
Yeah.
Okay. I agree. So I agree. So it's
So there's a group in Germany that has a set of images with no noise.
Okay.
They downsampled and filtered, so the
Okay.
ground truth is really, really noisy.
But here, clearly, it's related to the intrinsic noise of your image, because in Simpsons, for instance, I created the image myself, and I downsampled a lot to remove as much noise as I could. And the shift here, it's much smaller than the shift for Lena. So clearly.
Is it noise or is it could it be texture that is seen as interesting?
No, I think it's.
Because it's also in the.
You have in both images you have large flat regions. So I think it's noise. You have also texture in Lena, but I'm not sure. Yeah.
One more question.
If you know what it comes.
Yeah, okay. No, you're asking the coffee break there.
I'll ask it.
Okay.
Okay.
Good. So in the sake of time, we thank you again.